Thermodynamics by Simon Dawson. Okay, so first we're going to be talking about latent heat, vaporization, and fusion. And what this is that it's basically the amount of energy, which is usually heat, that's needed to change the state of a material. So if you look at the graph to the left, you can see that as energy is added to the material, the temperature begins to increase. But as the state starts to change, the temperature becomes constant. And then as soon as the materials finish changing states, the temperature begins to increase again. And this is because once the material has enough energy and reaches latent heat of vaporization or fusion, then the energy within it starts to focus on creating or breaking bonds within the material to allow it to change state, rather than focusing on increasing the temperature of the material. In my experiment, I set a cup of ice water on a hot plate and recorded the temperature as energy was added to the ice water. And as you can see, as the ice starts to melt, the temperature becomes constant and it's just going straight up. But as soon as all the ice is finished melting, the temperature begins to increase again. Now we're going to be talking about Gibbs free energy. And what this is that it's a way of calculating whether or not a chemical reaction will be spontaneous. So you use the equation delta G equals delta H minus T times delta S. So if G ends up being less than 0, it'll be spontaneous. If it ends up being more than 0, it won't be spontaneous. And if it equals 0, then it's reversible, or that the equation is actually at chemical equilibrium. In the equation delta G equals delta H minus T times delta S, there's three components besides Gibbs free energy. Delta H is enthalpy, and that is basically another term for latent heat of fusion and vaporization. There's delta S, which is entropy, and that is the measure of disorder in a material at an atomic level, so basically how disordered the atoms are. And there's T, which is the temperature at which the entire reaction occurs. Finally, we're going to be talking about thermal equilibrium. And this is the temperature at which two materials of different temperatures meet. And the law that correlates with this is the first law of thermodynamics, which is energy cannot be created or destroyed, only transferred. And there are ways to calculate what the thermal equilibrium will be, and that is Q equals mc delta T, or Q equals negative Q. So to calculate the amount of heat transferred, that would be Q equals mc delta T, and then since the two materials are going to meet at the same point, how much energy the first material loses, the other material will gain. And that's why Q equals negative Q, because one will be gaining energy and one will be losing energy. And so the components of the first equation, Q equals mc delta T, Q is the amount of heat transferred, m is the mass of the material, C is the specific heat capacity of the material, and delta T is the change in temperature of the entire reaction. At the beginning of the unit, the class did a lab to try to test thermal equilibrium, and what we did was we had two large glasses of water. One was on the table and was about 21 degrees, and the other was on a hot plate. And what we then did was we had 5 different materials at different weights and put them into the almost boiling glass of water to increase the temperature of the metal. And once we let it sit into the hot glass of water for about 30 seconds, and then we put the metal into the cold glass of water and let it sit there for about 10 seconds. After 10 seconds, we took the new temperature, and from that we were able to see how the metal ball decreased in temperature and the water increased in temperature until they met at the same temperature. And that is how we tested thermal equilibrium.